G'day everyone, Mr. Hanna here. This is the first video in our probability series. Probability is an interesting topic. Interesting because it relates to some real life situations, and also because lots of the stuff we're going to do, you can probably just think about it and work it out just from intuition. But in this chapter we're going to be learning to write it down a bit more formally than that. This first video is dealing with probability basics. It should hopefully be a revision for most of you, but it's super important that you understand this stuff really well before you get into some more complicated things. So let's start from the very beginning, which is talking about sample spaces. Now a sample space is basically just a list of all of the possible outcomes. Of all possible outcomes. So, for example, if your little probability experiment is choosing a random number between 1 and 10, so choosing a number between 1 and 10, our sample space, which has this weird symbol, our sample space will just be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now in other years, instead of using this fancy symbol, sometimes you just use a big S to represent the sample space. But we're mostly going to get practice using this annoying weird symbol. So another example, if you've got a bag full of marbles and you've got 3 red ones, so that means it could be, there's 3 red ones, there they are, or it could, and you've also got 2 blues in there, here they are, then that would be your sample space. All the possible things you could get out. You could get out, the first red one, the second one, third one, or the first blue one, or the second one. So the sample space is just all your possible outcomes. You could even just list them in a different representation, like creating like a bit of a box to represent everything that could be in your sample space. So we'll label that with our sample space symbol. And so for our first one, choosing between numbers of 1 to 10, we just write them in anywhere. 8, 9, 10. So there we go. That box represents all our possible outcomes. Now the next thing we need to know about is something called events. Now events basically are talking about something that you want to happen and observe that happening. So if our sample space is this first one, we're just choosing randomly the numbers 1 to 10, our event could be, say, choosing an even number. So we label events with a capital letter. So if I say event A is choosing a even number, choosing an even number. Okay, so I could list my event A as all the even numbers, 2, 4, 6, 8, and 10. There we go. Or using this box representation, here's our sample space, which has all of the possible outcomes. And I'm going to use a big circle to represent our event A, the even ones. So in A, I'll put all the even numbers, 4, 6, 8, 10, and all the rest out in this sample space box, 1, 3, 5, 7, and 9. There we go. So hopefully you'll start to recognize this as a Venn diagram, which will become more obvious soon. Because I could in fact put in another event too. I could put in event B. So let's see, event B could be choosing a number smaller than 5. Okay, so in other words, my event B, a number smaller than 5, that's 1, 2, 3, and 4. So if I write that into my Venn diagram now, changing it slightly. So I've now got 2 events, event A and event B. And in this middle bit is where both things happen. So you notice that the 2 and the 4 are in both events. than 4, so they better go here. 2, 4. 1 and 3 are only in B, and 6, 8, 10 are only in A, and the ones that aren't in either of those are 7 and 9. They're in our sample space, but in neither of our events A and B. So there we go. There's how you write a few things down. There's also, let's remind ourselves of a few symbols as well that we've been using already. So there's this one that kind of looks like an N. That means intersection. Intersection. Or it also means and. Okay, so if we say events A intersection with event B, so it's like A is happening and B is happening, that's referring to this middle section here where both of them are occurring. So our event A intersection B is, or contains, the possibilities of 2 and 4. There we go. Okay, so now there's another symbol as well, which is kind of looks a little bit like a large U, and it means the union, which means or. Okay, the union means or. Let's have a look. Whoops. A union B is if the event A happens or the event B happens. In other words, anything that occurs in this shape here will be a part of it. So that's quite a few possibilities. 1, 2, 3, 4. Oh, hang on, I've just realised that I've missed one. The 5 needs to be out here. 3, 4, 6, 8, 10. So you go, there's a few elements in our union between A and B. Okay, there's a couple of last things to tell you, and that is the complement. So let me do this. A dash, that means the complement of A. Complement of event A, which means everything except A. Okay, so it sort of means not A. So let me show you that on this Venn diagram. It means everything here and here as well. This area is included. Basically anything that is not in this A space there. So anything that is not A, so A dash contains everything that's not A. In other words, everything that's not even. So it'll be 1, 3, 5, 7, and 9. And you can even use this complement in sort of complicated ways. Like you could do, if we had the A intersection with B, but then brackets with the complement, that means not A intersection with B. In other words, it means everything except for this intersection area. So everything that isn't 2 and 4. So in other words, that would be 1, 3, 5, 6, 7, 8, 9, 10. Everything except for 2 and 4. Because those are the two elements in that intersection part. Okay, so there are a bunch of definitions for you, and hopefully you've used those in the past, which will make it a bit easier to remember them. Now on to actually calculating probabilities. Calculating probabilities. Okay. So when we calculate probabilities, and what we're talking about here is probability is when every outcome is equally likely. So here it was just as likely that I'd choose the number 1 as I would choose the number 7, for example. So the way you calculate probabilities is the probability of whatever you're looking for, so let's say event A, for example, is the number of elements that are in event A divided by the number of elements that could come up, so the number of elements in our sample space. So it's how many possibilities are we looking for over how many possible things are there in there. So let's go back and look at how many things are in event A. Well, here's event A. We've got 1, 2, 3, 4, 5 elements in there. So the number of elements in event A is 5, divided by how many elements are in the total sample space. Well, if we count them up, you'll notice that we have 10 elements in there. So that will be 5 divided by 10, which obviously simplifies to a half. And that makes sense because event A was probability of choosing an even number. So obviously it's going to be a sort of a 50-50 chance there. Okay, let's do a slightly more complicated one. Let's do the probability of A union B. Actually, let's do the complement of A with union of B, A or B, but not A or B, because that's what the complement means. So let's check this out. It's the number of elements in not A or B divided by the total number of possible things. So obviously the denominator must be 10 possibilities. So we need to look for how many things are not in A union B. So let's remind ourselves, A or B is this whole thing here. So it's just 7, 9, and 5 that are not in there. So there's three elements that are not in it. So we go, our probability is 3 over 10. Okay, now I want to show you an alternative way of doing this Venn diagram here. And I'm going to do it instead of just using the numbers that could come up, or the outcomes that could come up. I'm going to do it using the probabilities in each different sort of zone. Okay, so we've got event A there. We've got our event B there. Okay, so we just calculated that outside we've got a probability of 3 over 10. And we also found this one, which is a half. Oh, hang on. No, we didn't. Okay, so in this little zone here, we have 2 possibilities. So that's a 2 over 10. 2 over 10, which simplifies to 1 over 5. So this bit in the center is 1 over 5. Now, we also calculated here that whole of event A is a half. So that means that whatever goes here plus a fifth must be a half. So that means a fifth plus what we're looking for has to equal a half. Okay, so we can work this out. Another way of thinking about it though is just counting up our results here. We've got 1, 2, 3 out of the 10, so it's going to be a 3 over 10 in there. And if you did this sum of 1 over 5th plus our 3 over 10, that is the same as 2 over 10 plus 3 over 10, which is 5 over 10, which is a half, just like we knew it must be. Okay, so similar for this area here. By the way, this area that we're looking for at the moment, this sort of gibbous moon shape, is we can write it as everything that's in B and, so and is like one of those, and not in A. Okay, that's what this zone is. So everything that is in B and not A. So in B and not in A is a way to write that in words. So this complement means the not. Okay, so in that zone we've just got a 1 and a 3, so that's 2 out of 10. So that's a 2 out of 10, which of course simplifies to 1 over 5. And there we go, we've got every single zone covered. Now something you'll notice, hopefully, is that we've got every possibility covered. We've got out here where it's not in either A or B. We've got here where it's in A but not in B. Here where it's in A and in B. Here where it's in B and not in A. So we've got all of our bases covered. Let's see what happens if we add those probabilities together. We have the 3 on 10 plus the 1/5 plus another 5th plus another 3 on 10. Let's convert these all to tenths. 3 on 10, plus 2 on 10, plus 2 on 10, plus 3 on 10. So we've got 3, 4, 5, 6, 7, 10 on 10, which equals 1. And that's absolutely no surprise, because if you add all of the possibilities up, like one of those possibilities has to happen. So our probabilities, our total probability for any event at all occurring is always going to be 1. Because something needs to happen. When you pick one of those numbers, you have to have picked either, you have to have picked a number. So this leads us to a very important result, which is to say that the probability of the complement of A, so the probability of not getting an A, is 1 minus the probability of getting something in event A. So we can, or another way to write this is if you look at what the probability of the complement is, not getting A, and add it to the probability of event A, you get 1. Okay, because either A has to happen or not A has to happen, one or the other. And this is a very, very useful tool that will come in handy again and again. Because if someone tells you that if you already know that the probability of getting an even number is a half, then you straight away know that the probability of not getting an even number, that must be 1 take away a half, so it must be a half as well. Okay, so that's a very, very useful thing that you'll be using again and again. Okay, next thing. Alright, next thing I want to be looking at is tree diagrams. Now, tree diagrams are extremely useful whenever you have multi-stage events. Okay, so for example, let's say that you're spinning a spinner that looks like this. Let's say it's got 3 sections. They're all even. This one's red, this one's green, this one's blue. You're spinning that spinner, then you're rolling a die. Rolling a die. 6-sided, I should say. Okay, so that's what you're doing. And here's how a tree diagram basically works. So you list all the possibilities that you could get at the start. So obviously you could spin that spinner and get either a red, or you could get a green, or you could get a blue. And then you list what happens next. So then you roll a die, a 6-sided die, and you could get, after you get a red, you could get a 1, or you could get a 2, or you could get a 3, or you could get a 4, or you could get a 5, or you could get a 6. And then for green, you could get all of those 6 possibilities as well. And same for blue, you could get all 6 of those possibilities. And then you just write the probability of each thing occurring. So if you spun it to get a red, that's a 1/3 chance. 1/3. To get a green, that's a 1/3 chance. To get a blue, that's a 1/3 chance. And then for each of these dice rolls, it's going to be a 1 in 6 chance of getting each of those. 1 in 6. So all these are going to be 1 in 6, and same with all of these are 1 in 6. All of these are 1 in 6 as well. So then if someone was to ask me the question like, what is the probability of spinning red and then rolling a 2? Spinning red, then rolling a 2. Well, let's look. Here's spinning red, oops, there, and then rolling a 2, there it is. And a quick and easy way to work out the probability is multiply the probabilities. So to get the red, it's a 1/3, and to get the 2, it's a 1/6. So the probability is 1/3 times 1/6, which is 1/18. So there's a 1 on 18 chance of spinning red and rolling a 2. So that's an and. Spinning red and rolling a 2. Let's check out the probability of spinning red. Spinning red or rolling a 2. Okay, spinning red or rolling a 2. Well, let's see how many possibilities there are. If you get a red, that could be, it's a third chance that you get red. So it's 1 in 3. And it doesn't matter what happens here because they're all included. And then you'll add that to the possibility that you don't get a red, but you do get a 2. So there's this one, if you get a green and then a 2, that's a third times a sixth for the 2. So third times a sixth. And add on also the possibility that you spin blue and roll a 2. So that's a third times a sixth again. So what have we got? We've got a third plus an 18th plus another 18th. So overall that is 1/3 plus 2/18 is 1/9. So that is 4/9 of spinning red or rolling a 2. So it means you could spin red or you could roll a 2. Okay. Now, last thing, tree diagrams are very, very useful as well if your probabilities are not even. So let's think about the case where we have, say, we're picking marbles out of a bag. Marbles out of a bag. And not putting them back. Putting them back. Then choosing another. Okay, so we're picking marbles out of a bag, not putting it back, and then choosing another one. So overall we're choosing 2, I guess, but in order. So let's first look at our bag. Here it is. And let me sort of tell you that in this bag we've got 1, 2, 3, 4 reds and 1, 2, and 2 blues. That's what we've got. We've got 4 reds and 2 blues. So you can see that the probability of, at the start, the probability of choosing a red, probability red first, is going to be 4/6, or 2/3. And the probability of choosing a blue first is going to be 2/6, or 1/3. Okay, so let's set up our tree diagram. We could either get a red first, or we could get a blue first. And we get a red first with a probability of 2/3, and we get a blue first with a probability of 1/3. Okay, then we're going to choose the second one. So on our second chance, we could get a red or a blue. Okay, but things have changed now. So suppose we took out a red. So we've already chosen our red, so one red is gone. So that means our probability of choosing a red again is now 3/5. And our probability of choosing a blue is 2/5. Okay, let's think back to our other possibility if we had have actually chosen the blue all along. So let's put this red back in there. That red's definitely there. I'll scribble it out and put it here. But we had have chosen a blue first up. So we'll get rid of one of our blues. So now the probability of choosing a red second is 1, 2, 3, 4/5. And the probability of choosing a blue is 1/5. Okay, so here's our tree diagram is fully prepared, and now we can answer questions super easily. So if we wanted the probability of, say, red first, then blue, we can use our multiplying technique. So here's a red first, 2 on 3. multiplied by, then blue is 2 on 5, which gives us 2 times 2 is 4, 3 times 5 is 15. So that's a 4 on 15 probability for that one. Or let's do a trickier example. Let's say the probability of one or more blues. One or more blue. Okay, so it could be 1 blue or it could be 2 blues. So let's take a look. If we go, let's look at all the different pathways. We could get red, then blue. So this one here is a red-blue option. Or we could get this one, the blue-red option. Blue-red. Or this one, the blue-blue option. Okay, so those are the 3 options we need to consider. So first, the red-blue option is a 2 on 3 multiplied by 2 on 5. That's going this way there. Okay, next up is the blue-red option. So that's a third times 4/5. So plus a third times 4/5. And our last option is the blue-blue. So that's going at the third times 5th. 1/3 times 1/5. So let's see what we've got. We've got 4/15 plus 4/15 plus 1/15 gives us 4, 8, 9/15, which simplifies down to 3 on 5. So there we go. There's a big bunch of introductory probability for you. Make sure you are very familiar with all those things. See you later.